In this video we will talk about calorimeters. In this video we will consider two calorimeters, electromagnetic calorimeter and hadron calorimeter. Calorimeters are located after the tracking system and ridge detector because they stop all particles except muons. Electromagnetic calorimeter stops electrons and photons. All other particles fly further to the hadron calorimeter. Hadron calorimeter stops protons, neutrons and other particles containing quarks. In all high-energy physics experiments, hadron calorimeter stands after the electromagnetic one. There are only muon chambers are after the hadron calorimeter due to muons pass all detector systems. The calorimeters measure particle energies. They are based on similar principles but have differences in physics processes and composition. Let's consider each of these calorimeters more detailed. So, the calorimeter system is designed to measure particle energy. Particles interact with matter of the calorimeter and lose their energy. The calorimeter measures how much energy the particles lose before they stop. Let's start from the electromagnetic calorimeter. The electromagnetic calorimeter is responsible for measuring the energy of electrons and photons. Consider how the electromagnetic calorimeter works. Suppose an electron flies into the calorimeter. Interacting with the matter, the electron emits a photon and changes its own direction, losing some energy. After this first step, we have two particles, and sum of their energies is equal to the energy of the origin electron. At the second step, the photon interacts with the matter and decays into an electron and a positron. In the same time, the electron again emits other photon and again changes its own direction and loses energy. So there are four particles and energy of the origin electron is distributed on these particles. In other words, with each step the number of particles increases and energy of each of these particles decreases. This process repeats a lot of times and creates an electromagnetic shower. During this process, the number of particles exponentially increases, and sum of their energies is equal to the energy of the origin electron. So, energy of particles in the shower exponentially drops with each step of the process. Moreover, each step takes in average the same distance in the material of the detector. And as a result, particle energy in the electromagnetic shower exponentially drops with length of the shower. Let's formalize this. So, energy of a particle in the electromagnetic shower exponentially drops with its coordinates in the shower and proportional to the starting energy E0 for the origin particle as shown on the slide. In this equation, x0 represents average size of one step of the electromagnetic shower production. And this value depends on material used in the calorimeter. The more dense material, the smaller this value. This equation allows to estimate the shower size and number of particles in it. Let's consider that. Electromagnetic shower grows while the energy of the particles in the shower is above the critical value EC. The shower size X max can be estimated as shown on the slide. The critical energy EC as well as X0 in the equation are defined by the material of the calorimeter and width of the calorimeter and selected to be larger than the length of the shower. The total number of particles in the shower is estimated as follows. It's proportional to the energy of the origin particle E0 and inversely depends on the critical energy EC. Measuring the number of particles allows to determine the energy of the incoming particle. This number is measured by scintillation counters. Their signal is proportional to the number of particles flies through the counters. Consider composition of the electromagnetic calorimeters. In the high-energy physics experiments, electromagnetic calorimeters consist of a lot of crystals shown on the slide. The crystal creates an electromagnetic shower, and length of these crystals is selected to be larger than expected size of the shower. The crystals are transparent because a lot of particles in the shower are photons. Also, there is a scintillation counter after the crystal. It counts the number of particles in the shower. This number depends on the incoming particle energy, and this dependence is estimated during the calorimeter calibration process. In the LHCb detector, a lot of these crystals are collected in the matrix as it's shown on the slide. In the LHCb detector model, the electromagnetic calorimeter responses are represented as blue columns. One particle can activate several crystals of the calorimeters. Thus, it's needed to recognize a crystal cluster corresponds to the particle to estimate the particle energy more precisely. To do this, a particle track estimated in the tracking system is extrapolated to the electromagnetic calorimeter. Then, crystals close to the track in the calorimeter are grouped into a cluster, and sum of energies measured in all crystals of the cluster corresponds to the particle energy. Machine learning approaches can be used to recognize these clusters and estimate the particle energy more accurately. Moreover, photons are also create clusters in the calorimeter, but they no hits in the tracking system, and their tracks are not recognized. So machine learning can be used to recognize clusters for photons and separate them from clusters for electrons or just noise clusters. So electromagnetic calorimeters are also responsible for photons detection. Consider how calorimeters help to identify particle types. The equation on the slide represents the connection between energy, momentum and mass of a particle. We already know that the particle energy is measured by calorimeters. In the previous videos, we see that momentum of the particle is measured by tracking systems. So, using this equation, we can estimate the particle mass and, as a result, its type. However, in the next videos we will see how to use information from all detector systems to identify particle types more accurate. Now let's talk about the hadron calorimeter. As it was told in the beginning of this video, electromagnetic calorimeter stops electrons and photons. Other particles fly further to the hadron calorimeter, and hadron calorimeter stops protons, neutrons and other particles containing quarks. In high-energy physics experiments, hadron calorimeter stands after the electromagnetic calorimeter. There are only muon chambers after the hadron calorimeter due to muons pass all detector systems. The hadron calorimeter is responsible for measuring the energy of protons, neutrons and other particles containing quarks. The principle of the hadron calorimeter work is similar to the electromagnetic calorimeter one. But the incoming particle produces a hadronic shower instead of the electromagnetic shower due to interactions with the nuclei of matter atoms. This shower consists of large number of different particle types, not only electrons and photons. Number of particles in the shower exponentially increases with length of the shower. In the same time, energy of each particle in the shower exponentially drops, as well as for the electromagnetic showers. Hadron showers are larger than electromagnetic one, so the hadron calorimeter consists of several layers. Each layer has a layer of matter that creates an hadronic shower and a scintillation counter layer that counts number of particles in the shower. Unlike electromagnetic calorimeters, hadron calorimeters are use heavy materials such as metals. In the LHCb detector model, the hadron calorimeter responses are represented as orange cells. Similarly to the electromagnetic calorimeter, one particle can activate several cells of the calorimeters. Thus, it's needed to recognize a cluster of cells corresponds to the particle to estimate the particle energy more precisely. And to do this, a particle track estimated in the tracking system is extrapolated to the hadron calorimeter. Then, cells close to the track in the calorimeter are grouped into a cluster. And sum of energies measured in all cells of the cluster corresponds to the particle energy. And again, machine learning approaches can be used to recognize these clusters and estimate the particle energy more accurate. This is all about the calorimeters, and in the next video we will talk about the last system of the detector.